We found out that the probability of the union of the two events, getting garlic and contracting COVID-19, or, again, this is just probability of A union B. I invented an example for those who find it harder to kind of think about this in the abstract. Right, so this is, you're one of the people in this study. There's a 50% chance that you get the garlic treatment. We're in a situation where the treatment is not actually having any effect on the outcome of getting COVID or not getting COVID. And so if 20% of the people in the study wind up getting COVID within the year, that's going to be true for the garlic eaters and the non-garlic eaters. So the probability of getting garlic or contracting COVID is 0.60, because it's going to be the probability of getting garlic plus the probability of contracting COVID minus the probability of both, because we don't want to count the overlap twice, right? So it's actually everything in the to the 50% that's under A, that square, and then plus the extra little bit of B that's out in the A complement. Those are the folks who did not eat garlic and contracted COVID. So now we're moving on to the second question, which is, what's the probability of A complement intersect B complement? What does that mean in our make-believe example? It's the probability of not being given garlic, right? Being in the control group, not having to take garlic, and not contracting COVID, right? Where's that in the Venn diagram? Where is that intersection between not A and not B? Well, it's on the not A side, so it's on the right side of and not B, so nowhere in the that lima bean, in that oval, right? So it's everything to the right side of the rectangle that does not include anything blue, right? It's all this stuff. So what can we do to calculate it? Again, we only have a handful of rules. We had a few axioms and 2 or 3 theorems, and we're using these to figure out all these different kinds of combinations of two events: conditioning, intersecting, complementing, taking unions. So let's think about this. We know that we have rules for figuring out the intersection in general, where we could take the probability of A complement times probability of B complement given A complement, or the reverse of that. But we don't need to do that. Why? Because we know that if 2 events are independent, we just get to multiply to get their intersection. We can take the product of the individual probabilities. And we know that A itself is independent of B. I'm going to introduce a little notation that your book does not use. It's kind of like upside down pi. It's sometimes used for independent. Another one you may see is just a simple kind of upside down T. Sometimes that's referred to as A and B being orthogonal. If A happens, that gives you no information of whether B happens, right? Knowing that A happens does not change your probability that B happened. Okay, so if we know that the 2 of them are independent, we've already seen that that means the probability of their intersection is just equal to the probability of one times the probability of the other. So why would it also be the case that if A and B are independent, then A complement and B complement are independent? And that's true. So we're able to say the probability of A complement intersect B complement is equal to the probability of A complement times probability of B complement Think about why that is. I'm going to leave that as an open question, and maybe we'll revisit, or maybe I'll ask you to speculate it on a homework or exam. Okay. So we'll take that as given right there, that once we know that the two events are independent, then their complements are also independent. And so how do we calculate this? Well, we know probability of A is 0.5, so probability of A complement is 1 minus it, which is also 0.5, right? Probability of heads and tails. And what about probability of B complement? Probability of not contracting COVID-19 in the 1 year time period is 1 minus 0.2 or 0.8. So what do we got? We've got 0.40, right? 0.5 times 0.8. Let's think if that checks out. The probability of both not A and not B, right? We already said it's this kind of area over here. We know it's got to be less than 50%, which 40% is. We also know that there was a 20% chance of contracting COVID, and it's spread evenly over the garlic and non-garlic eaters. So the part that's over here on the right is the 10%. So that does kind of check out visually that the 50% minus 20% is going to give us the 40% number. Okay. Let's squeeze in the last one, which looks a little bit connected to the last one. Let's actually just jot down what we have. We have the 0.40. The probability of the intersection of the complements is 0.40, and the probability of the union is 0.60. We basically just took complements. We actually went along a roundabout way. If we noticed that that A union B, that what we calculated in that first piece, the probability of, plus the probability of what we calculated second, right? They should equal 1. We would have realized that if we recognized that A union B, its complement is the thing that we were working with the second time. It is the intersection of A complement and B complement. You can see that, right? What we calculated initially, we said was everything to the left of the dividing line, everything in A, right, plus this little bit of B that dipped into A complement. And the thing that we calculated the second time was the intersection of A complement and B complement, and that is everything that's outside of A and outside of B. Okay, so now we've got this last piece to figure out, which is the probability of A complement union B complement, the probability of not getting garlic or not contracting COVID-19, or both, right? It's an or, it's a union. It's anything that, I pick someone at random from the study, and is that someone who is not getting garlic or not contracting COVID-19 over the course of the year, or both? So let's see, probability of A complement union B complement, and our notation. What can we do here? What do we have? We can go back to our rule about how to calculate unions just from axiom 3, which says you take the probability of one of them, no garlic, plus the probability of the other, no COVID. Is that it? Now, they're not mutually exclusive. You can tell that they're intersecting one another, they're overlapping. Their intersection is not 0, so we have to subtract off in order not to double count. Probability of A complement. Oh, I'll give you intersect. I'll give you some of the other notation, right? Sometimes we see it just written as comma B complement, right? That's the same thing as intersect. And so that's equal to what? We did this addition earlier. A complement, probability of A complement is 0.5 plus probability of B complement is 0.8. Actually, I think we added something slightly different, right? But if probability of B is 0.2, then 1 minus that is the probability of B complement, and then subtract off this final piece. How do we get that? Now that was that I just kind of hit it a little bit by using different notation. That last piece that's subtracting off is the probability of A complement intersect B complement. That's what we did in part B, right? So subtracting off 0.4. That's equal to 1.3. Always feels weird when you're calculating probabilities and suddenly you see something bigger than 1, but don't worry, it's only because we double counted that 0.4, and so we get to 0.90. That just to, why is it so big? I've made a mess of the Venn diagram, but let's just go back to it for a second and see. Kind of just do it quickly. Right, so if we've got A on the left, A complement on the right, and we've got my B in here, what is the union of A complement, B complement? What are their unions? So we're talking about everything that's no garlic and everything united with everything that is, I'm sorry, that was yeah, that's right. Not getting garlic is this part on the right, and then the not contracting COVID is everything outside the blue oval, which also reuses some of this stuff on the right. So basically it's everything that is not in this intersection of garlic eating and catching. These are the garlic eaters who caught COVID, right? Everything outside of that 10% is what we're looking for here.